can add vectors together and multiply them with scalars. The closure property guarantees that we end up with another vector in the same vector space. It is possible to find a set of vectors with which we can represent every vector in the vector space by adding them together and scaling them. This set of vectors is a basis, and we will discuss them in the next video. Before we get there, we will need to introduce the concept of linear combinations and linear independence. So here's a definition. Let B be a vector space and a finite number of vectors x1 through xk be in V. Then, every vector v in V of the form v equals lambda 1 times x1 plus etc. lambda k xk equals the sum of lambda I xi in V with all the lambdas real numbers is called a linear combination of vectors x1 through x. The zero vector can always be written as a linear combination of k vectors because we can simply take each of the lambdas to be 0. We are more interested, though, in non-trivial linear combinations of sets of vectors to represent zero. That is, linear combinations of vectors where not all of the lambdas are 0, but yet sum to 0. So let V be a vector space, and x1 through xk be vectors in V. If there exists at least one non-trivial linear combination such that 0 is equal to the sum of the lambda I xi's, then we say that x1 through xk are linearly dependent. If no such combination exists, we call those vectors linearly independent. Here's an example. Is the set of these vectors 1, 2, 3, 3, 5, 7, and 5, 9, 13 linearly independent? Well, no, because 5, 9, 13 is 2 times the first vector plus the second vector. Now, the problem is that we discovered this by happenstance. It was kind of a fluke. So how do we determine linear independence or linear dependence in a more general way? Well, in general, if the vectors are not linearly independent, then we would have a situation where for one of the x's, lambda 1 times x1 plus lambda n minus 1 times xn minus 1 would equal negative lambda n times xn. Moving that last term, or the term on the right, to the left, that would mean that lambda 1 x1 plus everything up to lambda n minus 1 xn minus 1 plus lambda n xn would equal to 0. So this gives us a general strategy for how we can maybe attack this problem. The following properties are useful to find out whether vectors are linearly independent. K vectors are either linearly dependent or linearly independent. There's no middle ground or third option. If at least one of the vectors is 0, then the system is linearly dependent. The same holds if two vectors are identical. Vectors are linearly dependent if one of them is a linear combination of the others. So in particular, if one vector is a multiple of another vector, then the set is linearly dependent. One practical way of checking whether vectors are linearly independent is to use Gaussian elimination. Write all the vectors as columns of a matrix A, perform Gaussian elimination until the matrix is in row echelon form. We don't have to go so far as reduced row echelon form here. The pivot column indicate the vectors that are linearly independent of the vectors to the left. Note that there is an ordering of vectors when the matrix is built. The non-pivot columns can be expressed as linear combinations of the pivot columns on their left. all column vectors are linearly independent if and only if all columns are pivot columns. If there's at least one non-pivot column, the columns, and therefore the corresponding vectors, are linearly dependent. Here's an example. We want to determine whether this set of vectors, 1, 2, negative 3, 4, 1, 1, 0, 2, negative 1, negative 2, 1, 1, are these vectors linearly independent? Well, as we said before, let's check to see if lambda x1 plus lambda x2 plus lambda x3 is equal to 0. So we put these vectors in the augmented matrix, reduce it, and come up with 1, 1, negative 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. Now each of these columns is a pivot column, which means the vectors are linearly independent. We return to one of our previous examples. We want to show the vectors 1, 2, 3, 3, 5, 7, and 5, 9, 13 are linearly dependent, this time using Gauss elimination. So again, we check if lambda 1x1 plus lambda 2x2 plus lambda 3x3 is equal to 0. We create our augmented matrix, row reduce it, and we notice that column 3 is not a pivot column. Because we have that the last column is not a pivot column, these vectors have to be linearly dependent. In our next video, we're going to discuss the link between linear independence and the idea of a basis.